There's two kinds of aliens in the universe, the kinds you can see and the kinds you can't. So we just postulate there are some kinds of aliens that would just be pretty obvious. That is, they started somewhere, but then they expanded and kept expanding. And in the volume they expanded to do, they changed things. They did stuff. We don't know exactly what they'll do, but just like humans and life on Earth has changed stuff wherever it goes, they would change stuff. And if they do that to a big enough volume, they would be noticeable. And so we can think about what our data says about the obvious ones in a much easier way than we can about the other kind, the quiet ones. So we can come back to the quiet ones, but we're first going to focus on the big obvious ones.
Okay.
And
It's a little bit closer.
And the key point is we don't actually see them, right? They would be big and obvious and we don't see them. But
Right.
if we think carefully, we can figure out a lot about what that implies. You might not realize that it says a lot that we can't see them. So what we have is a 3-parameter model of where aliens are in space-time, and each of the parameters can be fit to data. And then you kind of need to believe this model to explain why we're so early in time, which is one of the key data points, our current date. And so, I'm happy to walk through if you want.
Yes,
Telling you
absolutely.
each of these parameters.
Austin,
and how
you
we
should
fit
be able to pull up some sort of graphics that represent this this concept and this study. Let's go through that.
We are here at 14 billion years into the history of the universe. That sounds late. 14 billion years seems like a long time, but it's actually pretty early. The average star will last for 5 trillion years. Now, the peak of star formation in the history of the universe was like 4 billion years after the initial. So we're well past the peak of star formation, but most stars will last for trillions of years. And so we are early in terms of when most stars will exist. And we have a simple theory of when advanced life should appear that says that the most likely time for advanced life to appear would be much later in the history of these stars. So I've told you about how life on Earth had to go through a number of difficult steps.
Yes.
And that Earth is probably lucky in having gone through all of those steps in an unusually short time. That is, most planets out there never get to our point before that planet ends.
Right.
Or certainly by now in the history of the universe. So that suggests that it's just hard to do each of these steps. And perhaps each of the steps just has a crazy long expected time, but that our planet got lucky. So an analogy is cancer. In your body, you have many billions of cells. And to produce cancer, a cell needs to undergo like 6 different mutations in that same cell in the entire history of your life. Now, these mutations are so unlikely that most of your cells never have any of these mutations, and only a few have a couple of them. But by the end of your life, typically one of them will get all 6 mutations. And that's analogous to all these planets in the universe who need to go through a bunch of steps to produce advanced life. And most of them never even get to the first step, and hardly any of them get to, 4 steps. And maybe our life got through all 6 steps to get to where we are before the deadline of life closing on the planet Earth. So that's like a cell in your body getting cancer before the deadline of your lifespan ending.
In other words, planet Earth has developed malignant cancer.
Right, although this cancer is great.
Depends on how you look at it.
Sure, but I'm going to take that stand. This life is great. But so what we know is that the chance of you getting cancer as a function of time goes as a power law in time, where the power is the number of these mutations that have to happen. So typically around 6.
Okay.
So you are far more likely to get cancer near the end of your life than the beginning. It's not constant in time. The chance just increases dramatically toward the end of your life. It goes as this power law of the power of 6 of time, because there's roughly 6 mutations.
Okay.
So similarly for planets, if advanced life like us is going to appear on a planet like Earth, it's not equally likely to appear at any moment in the history of that planet. It's far more likely to happen near the end of that planet's life. And it actually seems like there's roughly 6 hard steps that need to happen on a planet like Earth for us to produce life at our level as well. So that means over time, the chance of advanced life increases with time.
Right.
Now, but longer lived planets, they've got a lot more time for all these hard steps to go in. And so the actual chance of life appearing on a longer lived planet also increases by this power of 6. So we are a planet with, say, 5 billion years life, and say the typical planet out there will have 5 trillion years of life. That's a factor of 1,000 more. And if there's 6 of these steps, the chance that life would appear on one of those planets till the end of its life compared to our planet at the end of our life is 1,000 to the power of 6, or 10 to the 18. That is, it's crazy unlikely for life to appear on a planet like ours so early in the universe compared to on a longer lived planet later in the universe. So there's something wrong with this analysis, because our analysis is saying we are just crazy early.
Sorry, pull that thing just a little bit closer to you. You can adjust, you can pull it like this. Pull it closer. There you go.
So we're just crazy early compared to when we should expect life to appear. But the key assumption we made in this analysis is that the universe would just sit empty and wait until we appeared. And that's the assumption we're saying is wrong. So what's actually happening is life is popping up and appearing in various places in the universe, advanced life, and then sometime it becomes grabby, it becomes visible. And when it becomes grabby, it expands at some speed. And then these civilizations appearing at different time expand, and then their expanding waves eventually meet each other. And then at that point, the universe is full of grabby aliens. And then it's too late after that for life like us to appear. So there's a deadline in the history of the universe. First, the universe starts out empty, and then advanced life starts to appear, and then it expands, and then fills everything up, and then too late, you can't appear anymore. And that's the explanation for why we are here so early in the history of the universe. We are now at a period where the universe is filling up with aliens, and in 1 billion years or two, it'll be all full, and we couldn't appear 5 trillion years in the future because it will have long since been full then.
So we are just extremely early compared to other solar systems and other...
We're extremely early compared to when we would have appeared had the universe just waited empty for us. The universe is not waiting empty for us, is the key point. There's a deadline, and that's why we're appearing so early.
Okay.
So that's the first thing to say, is this is why you need to believe in this theory, is that we are crazy early otherwise. You have to believe there are aliens out there, and they are filling up the universe right now. And in fact, right now, roughly half the volume of the universe is full of alien civilizations that we can't see. And in another few billion years, it'll just all be full. And we may well soon join them, i.e. going out and expanding and becoming a grabby alien civilization. So this model of aliens appearing has 3 key parameters. First, we're going to assume they just appear at random places in space on the large scale of the universe. The universe is pretty similar. They just appear in a random galaxy, say. And then they expand at some speed after they appear. So that's one of the parameters. How fast do they expand? And then the other 2 parameters are when they appear in time. So I told you there's a power law. That is, the number of hard steps makes them appear later in time more rapidly according to a power law. So a power law has 2 parameters. It has the power and it has a constant. And so these are the 3 parameters that we can fit to data. So the power comes from the history of life on Earth. That is, the timing of when life appeared on Earth and how much time we seem to have left from now, and other data we have suggests there's roughly 6 hard steps on Earth, therefore a power of 6, roughly. Somewhere between 3 and 12 or something, but roughly a power of 6. The constant of the power law comes from our current date, because we are a random sample of when a advanced civilization appears. That is, we're not advanced enough to become grabby yet, but if we do so, it'll be within 1 million years or so. So
1 million years,
which is short time on the scale of 14 billion years. So relatively short time from now, we will either become grabby or not. But that makes our data a random sample from when these things happen. So that gives us the constant in front of the power law. So we have the constant in front of the power law, we have the power of the power law, and all we need is the speed of expansion, and then we've got the whole model. So how can we get the speed of expansion? Well, if you run this model and simulate it, you find that when civilizations are born and they look in the universe, we ask, can they see other civilizations in the universe? And what we find is if they expand slowly when they're born and they look out, they see lots of other civilizations. Huge, spherical volumes in the sky, much bigger than the full moon, full of aliens.
Spherical volumes in the sky.
Well, because they start at some point and they expand spherically away from there.
Okay.
And so you would look in the sky and you'd basically see vast spheres of alien civilizations. If everybody grew slowly, that's what the typical civilization would see.
Okay.
But if they grow very fast, most of them won't see any others when they're born because they don't see them until they're almost there. Because there's a selection effect, you couldn't appear within the volume of a different alien civilization because they would preclude you. That is, if they had born and using the volume, you would no longer be able to evolve there, at least if they so chose. So the fact that we don't see any aliens in our sky is the evidence that they must be expanding at a very fast speed, say roughly half the speed of light or even faster, which is extremely fast.
But it would explains why we wouldn't see them coming until they're actually here.
Till they're nearly here, but it might be millions of years before they're here you wouldn't see them, but still at a typical birth date, you won't see them yet.
Right. Okay.